In this section, we'll be looking at something called Eulers' method, which is used to approximate a solution to an initial value problem when we're dealing with differential equations. The idea behind the Eulers' method is if we have a curve, then we can approximate values using the slope at different points. So if at this point 0, I have a derivative that's giving me the slope, this blue line here, then I can guess if I take a small step that it would be about here. Since it's a curve, it's going to keep changing, but then maybe at this point I can approximate the slope and use it to estimate the next point, and at that point find the slope using our differential equation and use that to estimate the next point. Now as we get further away, we're going to be a little bit further and further away from our actual curve, and so this is only going to be an estimate, but since we're using really small values for those jumps, we may be pretty close to the curve. Now to do this, we're going to use a table that looks something like this. So the process for doing this might seem a little bit complicated at first. It's going to be something you're going to have to practice out a little bit so that you're ready to do it on tests. But you want to always draw this table so that you can show all the steps that you're doing, showing how you get from one point to another. Notice the table headings here. This is how we're going to set it up. We're going to start with whatever our initial point is, so x, y, and then we'll write whatever our starting point is here. The given value of dy dx at the point we're talking about. So we have an equation for dy dx, and we'll plug in this point xy to find out what it is. We're going to have delta x. Now this will be the same pretty much for our whole problem. Maybe we want to go by steps of x is 1/10 or 2/10 depending on how precise we want to be, how many steps we want to take, and so on. So our next step, once we know our slope of that line and we know how much x is changing, we can multiply those together to find out how much y is going to change. We then would add that change in our x and that change in our y to our original point to find the new point, how much it moved when we moved that little bit of delta x. We'll move that, we'll copy it down to the next line and then take another step. Okay, let's do an example. In this example, I'm given the differential equation x plus y, which is going to be this column here. I want to move by steps of 0.2. Now this is the only table that will be the only column in the table that will be the same for every step. Then we'll fill this in now. We want to approximate this value at 2.6. So if you notice, since we're starting at the point x equals 2, that means our next step would be 2.2. Okay, our first step is going to be 2, 0. Which means our next step is going to be at 2.2 for x. We don't know what the y is yet because that's going to change. Our next step then would be 2.4, and then after we add that 2, it's going to end up giving us what we want. Okay, so looking at this first part, x plus y, that's going to give me, looking at our formula, 2 plus 0, x plus y, which is giving me 2. We multiply those together, okay, so to find delta y, we want dy dx, which we just found to be 2, times our change in x, which is that. And so our change in y is going to be 0.4. So we come back to our original point here. Our x is changing by adding that 0.2, the change in x. So we have 2.2. Our y value then will be 0 plus the value we just found. We're now at 0.4. We then bring this value down here. We've just added to our x. We've also found how much to add to y. We do the same, repeat the same step again, except this time we have new x and y values for the first step, which will give us 2.2 and 0.4, which gives us 2.6. That's our dy dx now, 2.6. Our delta x is still the same, 0.2, and multiplying those together, I'm going to get 0.52. Okay, we then add from this, our change in x is now 2.4, because we're adding 0.2 again. And then the change in y, we're adding 0.52, which adding to 0.4 will give us 0.92. We bring that value down, our x we added already, so now 0.92. We add those values again, so 2.4 plus 0.92, because our function was x plus y, which is going to give me 3.32. And doing that, multiplying those again to find our change in y. And then we'll plug that in. Notice this time that takes us to 2.6 when we add our change, which is what we're looking for. And y is about 1.584. And this is only an estimate, again, because what we're doing is we're following this curve, but we're using these slopes and lines, which each time is going to get us a little bit further off of the graph. But since we took small steps, it's probably pretty close to the actual value. Now notice also in your book example for this problem, they wanted to go all the way to 3, which means they had to go 5 steps. So sometimes you might have to take a lot of steps to get what they want. In the next example, we're actually working backwards. Notice that they started us at x equals 2, y equals 3. So our initial point 2, 3. We're now following a different equation for our dy dx, 2x minus y. And we want those values to go with increments of 0.1 for delta x. But notice we need to work backwards here. We're going from 2 back to 1.8, which means our changes in x are actually negative. So we'll start by plugging this in. So 2 times 2 is 4 minus 3, which gives us change in dy dx is 1. And so our delta y is just going to be that negative 0.1 on our first step, giving us a point of, so 2 minus 0.1 is 1.9. And we'll bring that down and repeat. Again, we're plugging in 2x minus y, which gives us this time 0.9. Our change in x is always going to be 0.1 because that's what we decided. And this time multiplying, we're going to get negative 0.09, giving us a point of, okay, x is still going back 1/10, but y is going back 9/100 this time, 2.81. We can stop here now because that's what we were looking for. If we needed to go further, we could keep taking additional steps. But this right here will answer our question.